And we're back. Welcome back and happy Thursday. Today, we will continue on with our conversation of descriptive statistics, but we will focus this time on descriptions of distributions. Before we begin some administrative bits, the reading by the 5th of February, this Friday, please make sure you have read section 8.3. That's pages 230 through 239. Not a lot of pages, but it will still require your regular engagement. Homework number 1 is due Friday, the 5th of February, this Friday, at 9 o'clock in the morning. Please note that down. It's not the usual 11:59:59 seconds. It is Friday morning at 9 a.m. So when we last spoke, we talked about the relationship between the median M and the mean mu, and we can use that relationship to say something about the shape of the distribution in question. And so we said that the distribution is symmetric if the median equals the mean. It's skewed right, so it tails off to the right if the median is less than the mean, and it is skewed left, tails off to the left, if the median is greater than the mean. We also generalized the median and used this generalization to describe a set of points that chopped up the total probability mass for your distribution into equal sized parts. The 25% partitioning we called the quartiles. We had Q1, Q2, and Q3. And we used this to express synonyms for the median. Then we also looked at an application of the quartiles, specifically the sample quartiles, to do a semblance of outlier detection. And so if you have your sample quartiles, so that's from a sample data, it's a sample statistic, it's an estimator, we arrange the points, sort them in non-decreasing order, and then we identify the quartiles. So here we have samples with values 1 through 12 in non-decreasing order, and we mark off Q1, the 25% point, Q2, the median, and Q3, the 75% point. And so we compute the interquartile range, which is Q3 minus Q1, and we take 1.5 of that, and in this example, 1.5 IQR hat is equal to 9. And so we identify then that range of values that are 1.5 IQR hat below Q1 hat and 1.5 IQR hat above IQ3 hat. And so when we do that for this example, we get the interval from -5 to 19 on the integer number line, and we said that within 1.5 IQR, above and below the first sample quartile and the third sample quartile, that represents 99.3% of the population values. And we can use that quite efficiently to perform outlier detection. So let's take a look at another visualization method. And I agree, statistics, I think they're beautiful, all sorts of beautiful theories about. But there's no substitute, as you're finding, to look at your data, see what the data is telling you. So you're going to need a visualization, and doing that visualization properly is going to reveal all sorts of pattern phenomena about your data. And that's a key step if you want to understand the process from which you obtain that data. For example, you can get a probability distribution, look at its shape, and determine what statistical method might be appropriate. You can tell things like if outliers are present, if there are any temporal-based phenomena in play, if there are general trends or patterns, and look at even relationships between variables with the right visualization. And so a histogram is a very popular one. You've been using it all last semester in stochastic computing, and it visualizes the shape of the probability mass function or density function governing your data. And you can use it to do all sorts of things, including identify whether your data is homogeneous, relatively small variability, or if it has outliers, if there's some point that is very different above and below what is typical of the values that you measure. And so the procedure for computing a histogram, outside of just calling histogram in Matlab, makes it easy, I agree. But the procedure, if you were to do it yourself, is to define intervals for values, called bins of equal size, and then to iterate through all of your data, placing each data in a bin corresponding to the range of values in which it falls. And so then you maintain counts for how many data points values fall within each of the intervals. And so this is in the book, and on the left-hand frame, we have a so-called frequency histogram. Now, along the horizontal axis, and let me set my pen here. Blue seems like a good color. Along the horizontal axis, we have the bin center value. And so you represent each bin based on the center value within that range of values. And then along the vertical axis, we have the counts. And so here what we can see, okay, for this first range, between about 0 and looks like 14 or so, we have one of those. And then between 14 and 28, we have 5 of those, and so forth. And so this frequency histogram depicts counts of data points that occur in each bin. And the shape of it looks like the envelope for your distribution. If I direct your attention to frame B, this is the same type of information, but we've normalized it, a relative frequency histogram. So it's the same deal, but instead of depicting the counts, you're going to divide the count of each bin by the total number of samples that you have. And so the vertical axis is going to change in the case of a relative frequency histogram. That's going to represent precisely a probability because it's the total number over that proportion that's in a certain range. And so this relative frequency histogram depicts the same shape as the frequency histogram, but this vertical axis is a probability of a data value, a measurement falling within the range identified by the edges of each bin. All right, so let's take a look at different histograms associated with different distributions. And Matlab, of course, as we covered last semester, has all sampling routines for all the various distributions that we've studied. And so this example, in frame A, we have the uniform distribution. We have the exponential distribution in frame B. We have the normal distribution in frame C. And then we have a mixture of normals in frame D. So let's try these. And in this case, we're going to try the uniform, exponential, and normal. And then after a few slides, motivating things, we'll try the mixture distribution. So let's transition to Matlab. I will meet you in Matlab. So we're in Matlab, and we have a few blocks of code here that are going to produce 50,000 samples from each of a number of different types of distributions. We're going to have a uniform distribution, going to have an exponential, and we're going to have a normal distribution. And so here we set parameters for the uniform. A parameter is 1, B is 10, and the number of bins for the histogram that we're going to use to visualize these distributions is going to have 20 bins. The default, of course, is going to be 10 bins. And so we start out, and for our uniform distribution, let's just run these and see what we get. So figure 1, that is our uniform distribution. Let me pull them aside here so you can see them. Figure 1 is our uniform distribution, and we can see for this 50,000 samples from a uniform, it's roughly straight across, and you'll find that you might need more samples to fill in all these slight deviations from perfectly uniform. But for all intents and purposes, it's good enough for things that you want to use it for. So that's our uniform. When we look to the exponential, that's figure 2. Let me pull that up front and center. The exponential, you see, has that decaying exponential form. Starts up, scoops down, all the way down. And if you depict a distribution for an exponential, you see that it resembles a shape quite well. So lastly, let's look at the normal distribution. Well, the normal distribution has that bell curve shape, and of course, if you had more bins, it would be more fine-grained, and you'll find for this normal to kind of fill in enough to look like a prototypical normal distribution, like we've discussed last semester, you'll find that you need many more samples to represent it well. So let's test this assertion. We said we have 50,000 samples. So let's change this 50,000 samples. Let's change it to 200,000. Right, which is quite a bit more. And let's change the number of bins this time. Let's change it to 30 bins. Okay. So when we have more bins, that means we're going to need more samples to kind of fill in these details. And so if we look at the normal distribution, again, we have the exponential distribution and we have the uniform distribution. So now that we have many more samples that we've taken, this uniform distribution, the bin counts get closer and closer to truly uniform as you increase the number of samples. Exponential distribution, if we look here, that exponential distribution, it always looks relatively good based on the number of samples, be they the smaller number or larger number. But we see the normal distribution, it looks really much nicer if you increase the amount of samples. So that's just to say, if you're trying to visualize a distribution using a histogram to analyze in a very coarse way what the underlying distribution for your data might be, you can use a histogram, but you want to be careful how many data points that you're going to need in order to fill in the probability mass associated with each of the bins that are depicted. All right, so let's go back to PowerPoint. I'll meet you in PowerPoint. So we're in PowerPoint, and this is just a takeaway that something as simple as a histogram will give you a good visualization, but you want to consider how many bins are appropriate and also think about how many samples you have, because if the samples are too few, this histogram is not going to give you a very good visualization. So what we didn't talk about was this last frame, frame D, a so-called mixture distribution. And this mixture distribution is called a mixture because it's a set of different normal distributions mixed together. And so if you imagine the envelope for these distributions, you have one normal distribution here, and you have another normal distribution here. And the means of the first one, it's mu1, and the mean of the second one, normal distribution, that's mu2. And so this mixture is a great way of modeling a so-called hierarchical population. So let's go back to our discussion about populations. We talked about the homeless population, and in our example, we hypothesized that our population of homeless is subdivided into subgroups that are categorized as the homeless veterans, homeless families, those who struggle with drug addiction, and the aged out foster children. Now, we made that simplifying assumption for pedantic reasons, but, let's run with it. So in this, let's imagine we have the following population parameters. Now, granted, ground truth, you don't have access to these, but for the sake of demonstrating what a mixture population is and how you might sample from it, let's just imagine that we knew what these population parameters were. And so they are, imagine, ground truth, 22% of the homeless population were veterans, 17% were families, 27% are drug addicted, and aged out foster children are 34%. And hopefully that all adds up to 100. Let's see, that's 34 and 20, 50, that's 61, that's 71, 78, that's 80 plus 20, that's 100. Okay, so we're good. Whew. All right, so let's go forward. So these are the parameters. And if we're going to model them, well, we know perhaps some measurement to quantity of interest for the veterans, it falls out like age as a Gaussian distribution. As a normal distribution is a synonym. And this normal distribution for the veterans has a mean, and it has a standard deviation, the square of which is the variance. Likewise, we have families. Let's say if you took a family and you average their age, that age measurement for each family would fall as a normal distribution. It has its mean and its standard deviation. Likewise, for our drug addicted, for 27% of the population, their age measurement has certain distribution. Again, it's a normal distribution. It has a mean mu3 and standard deviation sigma 3. And lastly, foster kids, 34% of the population, they have their own normal distribution governing their ages with a certain mean mu4 and standard deviation sigma 4. Now, of course, if we're going to do this, let's depict the distribution. Normal mu1 sigma 1 squared is the normal distribution governing the veteran's age. Likewise, we have one for the family's age, drug addicted age, and the foster kid's age. Now, how would we do this? Well, if we want to sample from it, we're going to have to put together this mixture ourselves. So now we're going to go back to stick breaking, And because it's 4 different normal distributions, we're going to select from among these 4 different normal distributions, and then based on that selection, we sample from the respective normal distribution based on which particular subgroup in the population we've selected from. So you have your stick breaking construction. 22% of the time, you're going to select the first group, the veterans, the second group, the families, the third group, the drug addicted, and the fourth group, the aged out foster children. And so these proportions define our so-called mixture components. And the mixture components tell you the proportion of the total population that is made up by a particular subgroup. So let's try this in Matlab. We will meet you in Matlab. So we're in Matlab, and we're in the file Hierarchical Population, and we start out defining some constants that are going to represent positions in an array corresponding to the various subgroups of the population. So we have veterans, families, drug addicted, and aged out foster children. And so the stick values are going to be the proportions associated with each one of these population subgroups. Veterans is 22%, families is 17%, 27% drug addicted, 34% aged out foster children. So then we normalize these stick values as we talked about in great detail last semester. And then we go through a number of iterations. And before we do that, in this case, 100,000 iterations, we are going to set, before we do that, these iterations, we're going to set the parameters for each of the normal distributions. And so for the group of veterans, that's going to be mu veteran and sigma veteran. That's going to be the mean and the standard deviation. And so I'm just making up these numbers that the veterans, the average age mu, for that governing normal distribution is 35, standard deviation is 5. Likewise for families, it's going to be 50 and standard deviation is 5. And then for drug addicted, just making up these numbers, 70 and standard deviation is 5. And then aged out foster children, let's say the mean age, ground truth, is going to be 18 and the standard deviation is 5. And so we start out populating an array with all the parameters, both the means and the standard deviations, for each one of those 4 subgroups. So we list out the mu's first in line 33, and we list out the sigmas, the standard deviations, on line 34. So then go through a loop, and we iterate over the random selection of one of these subgroups. And once we select one of these subgroups using stick breaking, we take that selection and we index into this parameter vector for all the mu's and the sigmas, and we select out that mu and that sigma corresponding to the particular subgroup, whether it's the first subgroup, the second subgroup, the third subgroup, or the fourth subgroup. So then we sample from a normal distribution based on the mu and sigma for that particular normal distribution for either the first subgroup, second, third, or fourth subgroup. And then we save off that age, and we continue that iteration. So some large number of times, specifically in this case 100,000 times, we're going to sample from one of 4 different normal distributions where their parameters are set as followed in the mu array and the sigma array. Okay, so let's save this and take a look at it and see what we get. So it's going to take a little bit because it's a lot of samples, and we're doing stick breaking 100,000 times. And this is what we end up with. This is a mixture distribution. And when we take the histogram of this mixture distribution, you can actually make out the envelopes of the 4 different normal distributions. And so here, that's one normal distribution. We also have another. Let's see if I can annotate this. No, I can't annotate it. Okay. So if we trace the envelope of each one of these peaks here, that's the first normal. This is the second normal distribution. This is the third normal distribution. and that's the fourth normal distribution. And so with a mixture distribution, as you get more and more components in the mixture, you're going to need more and more samples in order to get adequate coverage from each one of these distributions, especially if that proportion for the stick weight is very, very small. Okay, so with that, let's bring this down and I'll meet you back. And so that's an example of a hierarchical population, how you would generate one. But when you see the histogram, we actually visualize this mixture distribution. All right. So let's take a look at this interesting stem and leaf plot. Now, of course, there are many different ways and methods that you can visualize a distribution, and this method called stem and leaf plot is really just a quick and dirty way, something you could do on a dinner napkin to visualize a distribution. And so the stem is the first few digits or digit of a number, and the leaf is the immediate next digit. For example, suppose we used the tens place in decimal notation as the stem, and the leaf was the next digit, which is the ones place, going from left to right, so from most significant to least significant in that direction. And so in that case, if we look at the ones, well, here, this vertical bar, it separates the stem from the leaf, and the leaves are on the right-hand side, the stem is on the left-hand side. So here we have a 10, we have 20-something, and we have 30-something. So we're going to mark our stem 1, 2, 3, representing the 10, 20, and the 30. So then on the right-hand side of the bar, we draw all the leaves, or write the leaves. And so we have a 10 with a 0, a 10 with a 1, that's 11, 10 with a 5, that's a 15. So we write 0, 1, 5, and we write that in non-decreasing order. Likewise, for the 20s, that's 2, that's 21, plus 2, 3, plus 2, 5, and 2, 7. So we write 1, that's for 21, 3 for 23, 5 for 25, and 7 for 27. And then lastly, we have the 30s, 33, 35. So the stem is 3, and the leaf is 3, that's for 33, and then the leaf is 5, that's for 35. And if you turn your head 90 degrees clockwise, it'll look like following. It'll look like, well, here's your 1, here's your 2, here's your 3, that says 0, 1, 5, that says 1, 3, 5, 7, and this one says 3 and 5. So this kind of looks like a histogram. If you were to kind of color all these in, shade that one, put a bar here, shade that one, put a bar here, shade that one, it looks just like a histogram. It is a histogram because the height is each one of these digits, and so if you have a higher one, that's a bigger count, and these are like bins. And so a stem and leaf plot is basically a histogram turned on its side. All right, so let's have another example with this stem and leaf plot. You can compare multiple sets of sets of measurements. And here we have measurements from what we're calling location 1 and location 2. Now, location 1 is on the left-hand side. Location 2 measurements are on the right-hand side. And in this case, the stem unit is 0.01, 1 100th. The leaf unit is the next digit, that's 1 1,000th. And so if we look at the 100th place, that's 0, 1, 0, 3, 0, 4, 0, 5, is 0, 2. So there's 0, 1, 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, 7. And now, going to the left-hand side for location 1's measurement, we go to the 1,000th place for decimal. So we don't have a 0.000, so we leave that blank. But when we look at 0.01, well, that's the tenth. It's in this part of the stem leaf plot on the left-hand side for location 1 measurements. It's a 0.015, right? So we look for 0.01s, all those entries, and we see that there's only one, 0.015. So we write a 5 there. Now for the 0.02s, All right, well, we see, all right, there's a 0.028, there's a 0.02, there's a 1, and then there's also 0.02, and there's a 1. So we have 8, 1, 1 corresponding to that entry in the stem leaf plot for the 2/100th place, the digits that follow in the 1000th place. So we do that for all of the measurements in location 1, and those are off to the left on the screen. And then we do that in similar fashion for all the measurements from location 2. So let's take a look at the 0.00, right? The 0/100th numbers. So that's 0.00, let's see, 004, right? So there should be a 003, let's see, 0.003, there we go, 0.003. So there's our 3, it's in order numerically, and 0.004, so there's a 4 there. And so we do that for location 1's measurements off to the left and location 2's measurement off to the right. What do we see? Well, we see location 1 is a distribution that has a single peak, looks like a normal distribution, and location 2, it is a distribution that has 2 peaks, a little bit of probability here, and it has another peak right here. It's a bimodal distribution. And so you could actually kind of imagine turning these 90 degrees, and you'd have location 1 look something like this, and location 2 looks something like this. And so with this stem and leaf plot, it gives you a very quick and dirty way of comparing distributions in a very simple way between 2 different measurement systems. You know, location 1 is unimodal, location 2 is bimodal. Location 1 has a smaller variance, location 2 has a larger variance. Okay, so the stem and leaf plot, let's look at another visualization for a distribution, and this is called the box plot. And a box plot is intended to give you a quick high-level view of your data. And when you think about high-level view of your data, you're considered or thinking about the center of mass or the central tendency, how spread out your values are, and how big or how small your values can get. And so the center of mass, okay, that's the sample mean. The spread, you can depict those using the quartiles in a robust way. How big or small your values can get, well, that's just the order statistics, the min and the max. And so imagine you had a weather report, and they might say something like the following. Tomorrow, you'll be expecting average temperatures of 47 with highs of 55, lows of 32. Across your region, local averages are most likely to span between 50 and 44. So, you know, why might this be the case? Why do you talk about the variability in temperature? Well, because you have something called local climatic effects. So even here in Delaware, the region of Delaware in Dover that's closer to the coast, that's going to be warmer than the region of Delaware out towards Hartley, which is a little bit inland. And there's not that much distance geographically. It's only about maybe 10 miles or so, 20 miles at the most. But just in that 10 to 20 miles, you span some changes in temperature because of the local differences in the terrain and what's around, the so-called local climatic effect or microscale climatic effects. And so we have a 5-point summary, and this is in the Barron book, our main text, second edition. And the summary for the distribution consists of the min measurement, the maximum measurement, the first sample quartile, the sample median, and the third sample quartile. And then in this plot, that's 5 plus 1, that's the plus 1. The sample mean X bar is represented as a dot or a cross. And so this is represented visually as a so-called Box-Whisker plot. There's a Box-Whisker plot, and when we look at all the different parts of it, well, the edges of the box mark the interquartile range. And so here, the left-hand edge, that represents the first quartile, first sample quartile, Q1 hat. That's Q1 hat. The right-hand edge, that represents Q3 hat. And the distance between the two, the top edge, that's going to be the interquartile range. That's going to be 1 IQR. This vertical bar here, that represents Q2 hat, which is the sample median. Here's the sample mean. That's the plus sign. And if we take this, project it down, you can identify the value for the sample mean. The left-hand whisker extends out to the minimum value. That's the minimum. And the right-hand whisker extends out to the maximum value. That's the maximum. And so together, all of these tell you about the shape of the distribution. And so remember when we talked about the relationship between the sample mean and the median, we said if the median is less than the sample mean, that's a right-tailed distribution because it tails off to the right. So with these summaries from a sample, you can tell a lot from this Box-Whisker plot about the shape of the distribution. And so here's an example. We go back to a data set that we used when we calculated the sample mean earlier in this few modules ago. And we had n equals 30 randomly selected jobs from your system, from your CPU on your processor using the top command. And so there they are. We have 3 rows of 10. And now we're going to cast the distribution governed by these numbers. These are samples. And we're going to describe the distribution using a Box-Whisker plot. And so there it is. Okay. Well, if we take the sample mean x bar, that's 48.2. And if you look at where that cross projects down to this axis, that's going to be 48.2 and change. The minimum is 9, the smallest value. Well, if you project that down, that projects down onto the number line at 9. The first quartile, that's 34. So this left edge of the box projects down to 34. And then the median, sample median, is 42.5. This projects down to 42.5. That's the sample median. Q3, which is the right-hand edge of the box, that projects down to 59. And then the minimum we said was 9. The maximum is 139. But this 139, if you look at it, gosh, well, that's pretty far away from all the others. Let's check if it's an outlier. And if you recall, we said values that are above and below 1.5 interquartile range are suspected as and tagged as outliers. So you take the IQR, and this IQR is the difference between Q3 and Q1. So we have 59 minus 34. So that's 34, 44, 54, plus another 5 is 59. So that's 25. So the IQR is 25. IQR hat is 25. So 1.5 IQR, that's 25 plus 12.5. 1.5 IQR, that's 25 plus 12.5, that's 27.5. And so we take our 9 and we go 27.5 in that direction. And so that is 9 minus 27.5, right? That 9 minus 27.5, that is, let's see, 9 minus 7, that's 2, and another 2, so that's 18, minus 18.5. So we get minus 18.5 as one endpoint on the left-hand side. And on the right-hand side, that's Q3 plus 1.5 IQR. So that's 59 is Q3, and we add 27.5. So that's 59, that's 69, 79, 79, and 7. That's 86, 86.5. So that's 86.5, which is about here, exactly here, 86.5. And so here, 86.5 is out there, and we see that the maximum value in the measurements, that's 139. That's an outlier. And that outlier, if I've done this correctly, we reject that as an outlier. So 59 plus 27, 69, 79, 86.5. And so we know that this extreme value 139 is an outlier, and technically we could also reject values that are bigger than 86.5 as an outlier, but we're just going to reject that one. And so here, this 82 is less than 86.5. 89, we could technically reject 89. But we know for sure that this maximum value of 139, it is the max, but we mark that as an outlier with a dot because it is so much further away than this 99.3% of all the measurements. And so you'd call that an outlier. And so values above and below 1.5 IQR, above and below Q1 and Q3, those are outliers. And so we'd recast this Box-Whisker plot to extend this whisker up to 89 and not out to 139. And we would include this 89 and not reject it because essentially this 99.3, unless it's 100%, you don't know for sure if this 89 is rejected, but this 139 is so much more, it's definitely an outlier. Okay, so that's our Box-Whisker plot, and it's really important to note that this Box-Whisker plot, this distribution, if we look at the relationship between the median and the mean, well, the median is to the left of the mean, and therefore it's right skewed. It tails off to the right. And you can see it tails off to the right. You have a lot of these values of low probability out to the far extremes. And so it's right skewed. And we say that the left and right parts of the box represent the 25% measurement. That's the 25% here, that's the 50% here, and that's the 75% here. And the maximum element from the data is an outlier. This 139 is an outlier because it exceeds 1.5 IQR by a lot. It's very likely it's not going to be 100% in the set of examples that we have. And so this is not the same, this Box-Whisker plot is not the same as what's called a candle plot in finance. And a candle plot in finance represents 4 pieces of information, the high value and the low value that a security or stock reaches during the trading day, the open and the close. And so if you have a candle plot that's green, green means it's a bull market and it's rising, going higher. And candle plot in the red, it's a bear, it bears down. And so meaning that it falls during the day. And so the high is where the whisker is on the top, the low is the whisker on the bottom, the open is the edge on the bottom, and the close is the edge on the top. Now you might think, gosh, well that looks like a Box-Whisker plot kind of stood up on its whisker, standing up and down instead of lying on its side. It is not a Box-Whisker plot. It looks like it, but it's not. It is called a candle plot, and it's used in finance to represent for a bull day or bear day for security, whether it's a high, low, close, open. And so sometimes you see it as a high, low, close, open chart, but the formal name is called a candle plot, and a candle plot is not the same as a Box-Whisker plot. Box-Whisker plot depicts these measurements describing or summarizing a distribution. A candle plot, you could almost think of it as a distribution, but it's not really a distribution. It's tied to the trading window, when it opens, when it closes, what the price was, and what is the high for the day and the low for the day. All right, so with that, we'll end there. And as usual, please make sure you're staying up with the reading. Do not fall behind. It can catch away from you very, very quickly. So with that, look forward to your assignment submissions tomorrow morning. And please have a great weekend. And as usual, please stay healthy, stay safe, and I will see you on Tuesday.